Hello, everyone. Welcome to my talk. My name is Isis. I come from Greece. I work for Census. And if you're familiar with the VMware exploitation, you may have heard my name in the past because I gave some presentations a few years ago regarding VMware exploitation. So basically, today is going to be my journey of how I initially approached VMware and how I managed to find my first bugs and how I ultimately managed to find some exploitation primitives. So my goal initially was to develop a guest-to-host escape exploit for VMware Workstation 12. And basically, back then, I was already an experienced developer and exploit developer, and I already knew some low-level stuff. But my disadvantage was that I was not familiar with how virtual machines work. So that's why my first thing to do is to actually map the attack surface of VMware. And mind you that it's 2017, so that means that there is not enough literature of how regarding VMware exploitation. But I managed to find some resources. Specifically, the best resource that I found is actually a presentation called Cloudburst, presented in Black Hat, and which was the first public attempt for SVGA exploitation. SVGA is the virtual graphics device of VMware. And there's also another attack surface of the RPCI, another presentation. But I decided to go with the SVGA device. So before delving with the SVGA details, let me first give you a brief overview of how VMware works. So in VMware, there are three major components. The first one you can see on the top left is a userland application on the host. It's called VMX. And this application basically implements all the virtual devices. And the second major, so for example, the SVGA device or the virtual network adapter or the virtual hard disk and so on. The second major component is the kernel driver on the host operating system, which basically it acts as intermediary between the host userland application, the VMX, and the hypervisor. The hypervisor is the third major component, and its main responsibility is to pass the execution from the host to the guest operating system. All these three components basically work together in order for the virtual machine to execute properly. From an attacker's point of view, you are mainly interested on the VMX application because since it implements the virtual devices, that means that it has a lot of communication from inside the guest operating system. So that means that you can send input to the VMX application from the guest and hopefully hit a bug for a guest-to-host escape exploit. So SVGA device, as mentioned before, is the virtual graphics device of VMware. And the communication between the SVGA device implemented on the VMX and the guest operating system happens through some shared memory mappings, which are called SVGA FIFO. There is a very good paper published by the authors of the SVGA device that describes the internals of the SVGA device. And additionally, they also released some mini operating systems for internal SVGA testing. And those systems basically, when I started, I downloaded them, I compiled them, and I ran them in order to understand how the virtual graphics device work. More on this about later. So on the VMX application, there is a dedicated thread called the SVGA thread, which constantly polls those shared mappings, the SVGA FIFO, in order to retrieve commands sent by the guest user. And as you can see, so as you can see on the top, on the function, there's a function called process SVGA FIFO process FIFO, and this function basically retrieves the command from the guest operating system, and then it calls a function called dispatch handler. All of the SVGA commands have this SVGA command header on the top of the source code, and this header basically contains the index field, and the index indicates the command that was requested from the guest operating system. So on the last line of this source snippet is basically you can see that there is a dispatch table that uses this index field in order to call the appropriate handler on the host side in order to service the request. So the communication protocol between the guest operating system and the SVGA device is called SVGA 3D protocol, and it has at least 5 primitive SVGA objects. For example, a surface, a context, shader, and so on. Basically, there are at least 4 different operations for the SVGA objects you can see on the right list. And those are, for example, you can define a surface or you can destroy a surface. Memory objects, or mobs for short, is basically the only object that is not graphics related per se. And memory objects are used as a mechanism in order for to pass input, to pass VMware to pass input to the rest of the SVGA objects. So for instance, you can bind one SVGA object with a mob, and the underlying data of the mob will be used to initialize this SVGA object. On the other hand, readback, the final operation, is the opposite operation, and that means that when you try to read back, for example, a surface, that means the data from the host operating system for the surface will be copied back to the mob that this surface is bound with. So I have an example here for you to understand it better. On the first command, you can see this is basically the define surface command. You must provide, for example, to define a surface, you must provide a surface ID and some other graphics-related stuff, such as the format of the surface or the dimensions of the surface. And then you have to also define a mob. And apart from the memory ID, you also must define the PPN, which is the base, the third field, which is the physical page number. So this will associate some memory in the guest region with a specific mob. Then you can bind the next command on the right. You can bind a surface and a mob, and this will be used to initialize the contents of the surface with the contents of the PPN provided in the define mob command. And last one is the define surface, the readback operation. Simply you provide a surface ID, and the contents will be returned to the PPN of the mob that is bound with. Okay, this is some source snippets from the mini operating system that I mentioned before. And initially, in the beginning, I was modifying them and minimize them in order to understand how the SVGA device works and how graphics work in general. And by accident, while I was playing with them, I copied this line, this define surface command, inside the while loop. And then I compiled the operating systems, and then I ran it against VMware to test them, and this is what was happened. So as you can see, this is an access violation bug, and it basically, the CPU tries to read from the RDX register some memory, and this memory is unmapped, and basically this happens because Windows page heap is enabled on this run, so this will be probably some kind of free chunk, so this seemed like a use of the free bug. Immediately I start reverse engineering the VMware in order to understand what's the root cause of the problem. And eventually I lead up into this cast view get function. And this function takes a lot of input, and it uses that input to craft a buffer and pass it into a function which is called key create. This function will basically create a hash, a unique hash, and this will be used next in a function called cache lookup, which will try to look up an associated object with this hash in a hash table. If the object is found, then it will simply return it. On the other hand, if it is not found, it would allocate a new slot for the cache. It will then call one of these three functions, which is basically allocate a DirectX object, some graphics object. And then it will store it inside the cache slot, and then it will call cache insert. The actual problem exists inside the cache insert function, because this function basically tries to keep the hash table up to a certain amount of size. So eventually, as you keep inserting objects inside the hash table, it will start freeing, deallocating the least recently used objects. So, and that would probably create some dangling pointers inside the host application of VMware. So now that we analyze the bug, let's see how my modification actually triggers it. On the left, this is pseudocode that I reversed from the VMX application, and basically it contains all the references of the buggy function. And if you notice the last one function, it takes as an input in order to craft internally the hash, the texture state dot value. If you look on the right side, again, this is the snippet of the modified version of the media operating system. And you can see that it defines a surface, stores the value in a variable named texture surface ID, and then it calls an SVGA function called set texture state, and passes this texture surface ID as the value. And this value is basically the same as the one below on the left. So basically, due to the modification that now the define surface command is inside the loop, and that means that texture surface ID is going to be different in each iteration. So basically, the buggy function will always, in its iteration, basically, it will go called with different arguments, and that would forcing inserting new objects into the cache, and eventually free the least recently used objects, and triggering the bug. On the right, you can see this is basically the backtrace of the buggy function. It is called from the SVGA command called throw primitives. And at that point, I wanted to move from the mini operating system and develop a realistic exploit. So I wanted to trigger the bug from inside the Windows virtual machine. That's why I was reversing the SVGA handlers, the draw primitives, and the function that the draw primitives calls, in order to understand all the requirements to force the execution to go from the, to call the buggy function. For draw primitives command, I must define a context beforehand and also declare some vertices. And from the sub whatever command, which is called by the draw primitives, I must call the SVGA command send renderer targets and send texture state before calling draw primitives. So all of this, if I did all of that, I will be able to trigger the bug from a Windows virtual machine. Unfortunately, while I was developing the Windows kernel driver to trigger the bug from Windows VM, I noticed that the mini operating system provided by the authors of the SVGA and the new fresh Windows machine have something which is called hardware compatibility, which is basically a version inside the configuration of the virtual machine. And this number basically dictates what kind of virtual hardware is going to be used from the VMware. And since the mini operating system were old, that means the hardware compatibility was also old, and there was a difference in the SVGA 3D API between the mini operating system and a fresh new Windows virtual machine. So for example, drop primitives command is deprecated, and I was not able to call it from the Windows VM. However, I managed to find by reversing a similar command, the draw, which I was happy about that because they make the same things. And additionally, also the set texture state and set render targets were also deprecated, and I was not able to call them. But luckily, I was able to meet the requirements in order to trigger the bug from this define context command. So on the bullets, you can see the 4 requirements. And first, when I define a context, then which is basically I meet the first requirement. And then when binding with a mob this context and providing the data structure on the right as an input, you can see that basically I'm able to also provide the render targets, the vertex declarations, and the texture state, and finally meet all the requirements and trigger the bug from the Windows virtual machine. And this is a source snippet from the Windows kernel driver that triggers the bug. And I have a function which is called init and draw. And this function basically will do all the preparation that is required in order for the driver to call draw command and actually trigger the function and the buggy function and insert new slots into the hash table, and eventually start creating, when the hash table is full, start creating some dangling pointers. So the next step that I had to do is to find an interesting use of this freed buffer. So eventually, by reversing the draw command, I managed to found a function. This is basically the disassembly of the function. You can see the first instruction is the freed buffer, the use of the free buffer, and it tries to dereference the direct object that is stored inside it. And since it is a C++ object, this means that by dereferencing it again, it will take the vtable. And at that point, I knew that if I somehow managed to reclaim that heap chunk and call this and force to VMX to go from that specific part, I would be able to jump to an address of my choice. But again, by reversing, I managed to find another SVGA handler, which was called setShader. And below, you can see the reversed source code of this handler. And it calls a malloc, and the argument, the size in bytes argument of malloc, it's controlled by the guest. And the allocate buffer will be used as a destination for a memcopy operation. And the source of the memcopy is also fully controlled by the guest. On top of that, I'm able to call multiple times this function, so allocate many chunks into the heap. And also, those chunks will stay into the heap until the guest user calls a destroy command. So by combining all of this, I'm able to jump in an address of my choice. But now I have to defeat the ASLR in order to provide, for example, a ROP gadget to jump. So as mentioned in the beginning, the readback mechanism is basically the mechanism for VMX that for VMware that basically copies the contents of the SVGA object back to the guest user. And I thought initially that this would be a good surface to look for an info leak bug. And indeed, surface, the readback operation of surface is pretty complex due to the big number of formats for surfaces. And additionally, that throughout all the handler of the surface readback operation, it performs many mathematical operations using the dimensions of the surface. So I thought that this would be the ideal scenario for an info leak bug. So on Windows host, surfaces are represented with a data structure on the backend, which is called resource container. And the most interesting thing about this data structure is that it contains a buffer in which the contents of the surface will be stored. And on VMware 12, the version that was targeted, there are basically 9 different resource container types, and which type is going to be allocated, basically, it solely depends on the surface format. On the left, you can see the data structure of resource container type 9, and you can see that it contains the type, the format, dimension, some stuff from the surface. Also, it contains function pointers, which is interesting. And finally, it contains a pointer to buffers that will hold the contents of the surface that will be provided from the guest operating system. And on the right, you can see the constructor of the SVGA of the resource container type 9. And basically, it has a loop that it will calculate the size of the buffers, which are based basically on the dimensions of the surface. And then it will call this function called mks memmgralloc, which is just a simple wrapper on top of malloc in order to allocate the buffer. If you notice carefully, it forgot to zero initialize the buffer returned from malloc. So at that point, I thought, what will happen if I issue a readback operation in this surface and this resource container? And indeed, this is again some source code taken from my kernel driver. And at the beginning, I will define 2 surfaces, one source and one destination surface. Then I will call draw command in order for the VMX application to construct the resource container type. Then I will bind the destination surface with a mob. And then I perform a surface copy command. And this command will take the contents from the source surface, and those will be the uninitialized contents of the resource container type 9, and will copy them into the corresponding resource container of the destination surface. And after that, immediately, I will issue a readback operation to the destination surface, and that will lead to returning those uninitialized data from the destination surface back to the guest operating system. So I have an info leak here. But now I want to leak something meaningful in order to calculate, to basically bypass the ASLR of VMware. And that's why I did the following trick. The first step, I sprayed it with some resource container. Type is irrelevant here because I'm mainly focused to leak back function pointers in order to calculate the base address of VMX. Then the next step, I will free all of these resource containers, and then I will allocate a resource container of type 9. And I will be carefully while I'm calculate the dimensions of this resource container type 9, because I want that the data buffer that will be allocated when the constructor of the resource container is created to be equal to size as the resource container of the first spray. This will result into probably reclaiming a heap chunk from the resource containers in the beginning. And mind you that those resource containers have function pointer. And then by performing the readback trick, I'm able to basically lead back to the guest operating system those function pointers, which is like the last chain in the puzzle. And I'm defeating ASLR by this leak bug. I'm able to trigger the free spray with shaders to reclaim the heap chunk and finally execute arbitrary code on the guest operating system. So now, a few weeks later, actually, VMware released a new version of VMware Workstation, and as it usually happens, all of my bugs were patched, either probably due to some code refactoring or some kind of internal audit of VMware. But I really wanted to develop an escape exploit again, and I thought it would be a better chance because now I'm already familiar with the internals of VMware. I know where to look for bugs inside the SVGA device, and I'm also more experienced with the exploitation techniques. At that point, there was some discussion on blog posts and on the internet regarding some bugs on the SM4 bytecode parser of VMware. SM4 stands for shader model 4. However, while I was reversing the draw command for the previous exploit, I noticed that apart from the SM4 parser, there is also an SM3 parser inside the VMware. And I will confirm that I was able to reach from the guest operating system this parser, and I thought that it would be a good idea to try to look a bug over there because basically everybody else in the planet is looking on the SM4 parser that is discussed on the internet. So I thought the bugs that I will find in the SM3 parser, I'll hopefully stay alive longer. So without further ado, I started reversing the SM3 parser located in VMware. So on the top left, you can see basically the entry point of the parser. And it basically contains a loop. And this loop will parse the instruction, provide it into a buffer. And once the instruction is parsed, it will call this process SM3 function, which basically just a big switch case that it contains a handler for every of the bytecode opcodes that it encounters. We're mainly interested in the opcode 51 in hex. And on the bottom left, you can see basically this is the handler, which is called from the process SM3 instruction function. And after some basic checks, it will call this function sub whatever. And you can see that the pseudocode on the right. And this function will allocate using MKS memmgr allocate with tag function, which is just, again, a function on top of malloc, a fixed size buffer, and it will store it inside an object. And after that, it will store data directly from the bytecode provided by the guest operating system inside that buffer. And also, it will increase the value of an offset. So if this function is called again, then it will write at the next slot of this fixed size buffer. And yeah, basically, again, here there is a robust bug. And the bug is that since this is a fixed size buffer, if too many encounters of the 51 in hex opcode exist on the provided SM3 bytecode, that means that eventually I will be able to write out of the boundaries of this vulnerable buffer. So I have a classical heap correction bug with semi-controlled data. And I used, in order to exploit it, I used a low fragmentation heap attack, metadata attack actually. But it is out of topic right now, so I will not get into details. But the result I had from this attack was basically that I was able to leverage the bug from a heap corruption to actually write at a heap chunk of my choice. And at that point, I was thinking, since now I have a fully control over the heap chunk, which chunk should I choose in order to corrupt it and have arbitrary code execution. And that was the point that I realized the potential that resource containers have for an exploitation primitive. And basically, they have data buffers that are used for copy operations between the guest and the host operating system. They have function pointers, which I can corrupt them. And they I can also spray the heap with resource containers. And it really seems like the ideal data structure for using it on exploitation operations. And this is how I use the resource container in order to trigger the second bug. So I sprayed the heap with two different resource container types. The first one is RC1, or resource container 1, and the second is RC0. And different resource containers basically have different sizes. So that means that they will be placed in different user blocks. And I also was careful enough in order to calculate the dimensions of the resource container type 1. So the data buffer that was going to be allocated for the resource container of type 1 would be of the same size as of resource container 0. So the heap would be like as in the figure you can see. So the data buffers of resource container type 1 will be in the same user block as resource container 0. Then I will trigger the bug, corrupt a heap, and use the low fragmentation heap attack to control some heap chunk of my choice. And then basically, my idea was to modify the dimensions of the resource container type 1 and then trick VMware to think that the end of the associated data buffer to the resource container type 1 is actually bigger than it actually was. And then by performing a readback operation, I would be able to leak back to the guest operating system the contents of the resource container that is placed after the data buffer, as you can see in the figure. And for the exploitation for arbitrary code execution, so by doing that, I was able to leak the function pointers and defeat the ASLR, basically. And once I have defeated the ASLR, then the next step was to corrupt some of the function pointers. And basically, to do that, I could either use the metadata attack in order to corrupt the function pointers of resource container 1, or even write to the data buffer, actually after the end of the data buffer, to RC0, which basically would corrupt the function pointer or RC0. And by already have defeated the ASLR and corrupting function pointers, I'm able to calculate to actually execute arbitrary code on the guest operating system. So to conclude, targeting a complex software, especially if you're not familiar with it, can be really, really frustrating in the beginning. But if you have something concrete and something solid, as I did with the first bug that I discovered by accident, luckily, this can be a huge motivation, and it can guide you towards discovering the paths that are necessary to discover in order to understand the core and the architecture of the surface that you are looking to for bugs. And obviously, the more time that you spend on a specific surface, more efficient you will become to find new bugs, to go through the code faster. And finally, most important thing for me is to remember to be able to recognize reusable exploitation primitives and techniques, as they will be very invaluable in the long run for the future exploit that you will have. A real-world example are the resource containers that I mentioned throughout the presentation, which I discovered quite a few years ago, and I can assure you that they can still be abused as of today. That was the talk. Thank you so much for your time. So I think we have some time for questions, and I will also be at the wrap room after if you want to talk to me in person. I can hear you.
Using it with ESXi?
No, basically, because the bugs that I've looked for are for Windows operating system. I mean, the host that I want to, the bugs are specific on the code of VMware that exists on workstation for Windows operating system. So I never looked on it, but I would guess that the same bugs will not exist on ESXi. However, I believe that the rest of the doc regarding the exploitation primitives and the architecture in general would be relevant to ESXi as well.
Yeah, so can you talk about more, like how did you find that bugs? Like first one was like.
Can you talk on the mic? I can hear you.
Can you talk about more like what methodology that you used to find the bugs? I think first one was accidental, but you found more bugs, right? And the second is how did you reconstruct the symbols, like the function's name and the structures and all?
So to find more vulnerabilities basically is behind the idea that as you can, you are getting more familiarized with the assembly basically because it's closed source. You can tell which part of the code are written more carefully and which part of the code are more, or maybe which part of the code basically you can provide more input. And usually if you are able to provide input, you can, probably you will be able to find more bugs. So for me is actually that, for example, if you take a look at the second bug, which is the SM4 bug, SM3 bug, I noticed on the internet that there was some SM4 discussion, SM4 CVs from VMware, and I thought that since they are looking on for shader bytecode, then it might be a good idea for me as well to look them. And regarding your second question about the symbols, all of the symbols that you can see here are basically reverse engineered by me. So I was reversing VMware, I was trying to understand what was happening, and then I concluded into a specific name. However, I'm aware that this, at least there used to be, you can find it on the internet, that there used to be a version of ESXi for ARM that VMware forgot to strip it from symbols. So that may be a good starting point regarding to start looking for symbols. Yeah.
How long did this whole process take you?
Yeah. So regarding the first bug was something about 6-7 months, I would say, because my first time approach, as I mentioned, my first time approaching VMware, and I was not very good at knowing how virtual machine works. So it took some time. I think it was around 7 months in order to fully develop the escape exploit. And for the second bug, once I found the bug, which probably took me about a month or two, then after that, a month or two would be to develop the exploit, because I already knew the execution flow inside the VMX, and I already found the tricks with exploitation by abusing the resource containers. Okay, that's all. We are also out of time, so thank you so much.